they go out in the rain, they gotta have the hats on. So I'm pretty happy with that. I had kind of 100 here, and there's some distribution around there. And then there was kind of like 60 down here, and there was kind of a distribution down there. And you kind of end up with an average around 84. And so how we can do better, how I can bring this group up, and I don't want to bring this group down, but bring this group up. And the question is, why we have a distribution around 100, and why have a distribution around 65 or something?
Was up on the last legislature, they got the lectures up. That'll help some folks. I mean, if they understand what's going on in the class.
To go through the lecture again? Yeah, that's cool. So all the lectures are up now, or?
Yeah.
Today?
Obviously today's won't be, but yeah.
Yeah.
We try and do them, we're about a week behind, usually. Right, it's off the best side.
So we're under the math side, you go to the math side, then you have the physics down below. Is that the best way to do it?
Yeah.
Okay. Good.
How's the sound on it? Is it okay?
Everything's great. The only thing is like whenever you bring up the window and zoom it in, like if he writes a 7, it might show up as a 1. I mean, it's just still kind of choppy and stuff like that.
Okay.
But what you write, whenever you write it. I mean, like Mr. Tyler, I have him online for Calvin, and I watch all the lectures online and stuff, and he talks while he's writing. So I mean, what's on the board, but sometimes
So
the
I need
numbers
to talk
look-
to you while I'm writing something. Okay. I remember that.
I mean, it's better. The whiteboard's better than the old lectures he has on the chalk.
The other idea is if I'm getting 105, that means I might not be challenging the students. So got to come up with harder extra credit problems. What do you think? Average on a test. I thought I didn't think it was that easy of a test, so I'm pretty happy with the results. Any general comments? Let's go through it real quick. page number 1, any questions on the matching page? The very last match is kind of tricky, where I have average acceleration, initial velocity equals final velocity divided by 2. So that would be tricky, but then by process of elimination, if you did all the other ones, you'd probably end up with that, and you'd see the trickiness of it. Just another kinemax problem, just plug and chug, solve for the unknown. Second one was slightly tricky. I took that straight off of the problem set, and I don't remember if we talked about it or not, but they're just trying to Mike, and she's actually traveled a greater distance, but from the point of origin, she's traveled a lesser displacement. And I think just about everybody got that one. It was slightly easier if you did part B first for organic and falling. So then you find by using kinematic equation number 3, you could find her final velocity right before. And then once you find that final velocity, then you can use kinematic equation number 1 to find the time it took. And let's do that. Acceleration will be positive because we're going down. Velocity will be the square root of all that stuff. And that would come to 35 meters per second. And then final velocity. Minus 7, 9.8, 2.86 seconds. And some of you did part A first, which is fine. And if you do that, you end up with a quadratic formula. Here. And I guess probably, if I was nitpicking, I'd probably because you didn't show the original equation first. So I'll let you know now, when I say show all work, I want you to start from an equation. Three or 4 or 5 form, and then solve for the unknown. So I need to know where you're starting. Because some of these things, some of you can do them in your head after a while, and you can almost do all the calculation in your head, come up with an answer, put the answer down. And of course, I already. What you've done. So it's important to show your work. about any questions on problem number one? Versus distance and velocity as well. And again, I would stress showing your work. I mean, you could calculate that the total distance you travel is 1,300 meters, but you kind of want to show that. And even if you just actually put a D for your distance, and you just say anything, don't assume that it's obvious and it's 1,300 meters. Put 1,300 meters down as your answer and not show any work. Right? I mean, you gotta prove something. You gotta show it. Put in your time, which was 10 minutes. That's good. Or 600 seconds. So that would be the speed. Those three displacements as vectors, I mean, it looks something like this. You had vector A, which would be a negative 300I. And you had vector B, which would be 400J. And vector C, three. So if you actually did that, if you say your resultant vector is vector A plus vector B plus vector C, I equals 300I plus 400J. Remembering to put the hats on your unit vectors. And if you left it like that, that would be good enough for displacement. I mean, you could go one step further and you could find the magnitude and direction. So I said the magnitude of this, which would be 300 squared plus 400 squared, square root, 500 meters, and the direction inverse tangent of the y over the so it'd be 53.1 degrees from the positive x-axis. You always have to define your angle. If you come up with an angle, you have to define it from somewhere. So, if it's positive 53 or negative 53, you got to define where is it from. Instructors might just say, just define it from the positive x-axis. As long as you define it from somewhere, you can define it from the negative x-axis or the positive x-axis, then that defines it in my book. But you have to define it from somewhere. And this describes displacement. In other words, if you went this route, theoretically you would have to say what angle it was as well. And if you say magnitude and direction, because displacement's a vector. Now, I don't think I took off of that in the sense, because the next question that I did not take off for direction for your displacement if this is the route that you went, magnitude and direction. For what's the average velocity? In this case, that would be the magnitude of this r vector over time. Comes out to 0.83 meters per second, and then you would have the same angle, theta 53. What you could do is take that displacement vector here and just divide it by time. So you could say that your average velocity is your displacement vector divided by time. 300I, 400K, divided by 600. And again, that would describe the velocity, magnitude, and direction. That's your velocity vector right there. Any questions on this problem? This problem was probably the most. Problem number 3. Celebration of Australian Open tennis victory, Novak Djokovic slams a tennis ball straight up in the air. Number 3 in the world, but now could be number 1 pretty soon. Also known as the Joker, because he likes to make fun of the other players. Once in a while. All in jest. So, we're going to find the initial velocity. Velocity equals initial velocity plus acceleration times time, and in this case, the acceleration is the negative 9.8 meters per second squared, because he's hitting the tennis ball straight up, and that would be the direction of the initial velocity. Initial velocity we don't know. Final velocity is 0. And time is 2.5 seconds. So solve this for initial velocity. So initial velocity would equal final velocity minus acceleration times time. That would be 0 minus the negative 9.8. So 24.5 meters per second. One or two of you actually worked this problem kind of in reverse. You kind of said, we'll say initial velocity 0, and final velocity is the final velocity we have if we dropped it from the max. If you dropped it from maximum height, when it was about to hit, it would be the same as the initial velocity you would have to have in order to get it up to maximum height. Because the reverse motion is exactly the mirror of the motion going up. If you did it that way, though, you would have to say that you're doing it that way. Because otherwise, you're saying that your final velocity is your initial velocity. How high does it go? Final velocity squared equals initial velocity squared plus 2 times acceleration delta y. Acceleration. And that would be 0 minus 24.5 squared, or 2 times a negative 9.8. I think it came out 30.6 meters. And some of you actually checked that using your numbers and recalculated acceleration, which is good. You come up with the right answer. Any questions on number 3? The truck and the car. Cars stop at traffic light. Light turns green. The car starts from rest. Then accelerates at 2.5 meters per second squared. As light turns green, a truck passes the car at 50 meters per second. How long will it take the car to overtake the truck? Car, acceleration is 2.5 meters per second squared. We don't know the displacement. We don't know the time. And we do know initial velocity is 0. And we don't know the final velocity. We don't know displacement. Don't know time. Initial velocity is 15 meters per second, and final velocity is 15 meters per second. If we were to describe these two displacements, you would say that initial velocity being 0, so the displacement for the car would be 1/2 times 2.5 t squared, or 1.25 t squared. Acceleration times time squared. Acceleration being 0, so it's just going to be initial velocity times time, the average velocity times time, final velocity times time, 15 times t. Displacement of the car to equal displacement of the truck. So 1.25 t squared equals 15t. Or t is 15 divided by 1.25, or 12 seconds. So it'll take 12 seconds. Use either one. 15t or 180 meters. approaches to this problem, and one of the approaches was to find the truck. At the end of 12 seconds, the car will be moving 30 meters per second, and then kind of reverse engineer that. That kind of worked. A few of you figured out how much time it took the car to get up to the same speed as the truck, and I just automatically gave that half credit. If you get up to the speed of the truck, you're still far behind the truck. In fact, if that's the only thing you did, you'd always be behind the truck. Any questions on phone number 4? Five, 2 vectors. Slightly redundant. A lot of the chapter 4 stuff, so I kind of had to fit in more of the stuff from the first 3 chapters, and so you got a little bit more chapter 3 and a lot less chapter 4. Just writing these vectors, we had A equals I plus 5J. B equals 4I plus J. And again, if you're asked to do something, just kind of humor me a little bit. Actually, actually show A minus B equals something, rather than just, throw a number down there. This would be an easy one to do in your head, but you really need to show the word. Or later engineering courses where it'll be even more important to show your work. Come up with a negative 3I. Plus 4J. If you just missed a hat here and there, I probably didn't take out the point, but if you missed a lot of hats or a lot of arrows, took out the point because vectors are. Components add together, square root. Y over X. Of course, this one would be from the negative x-axis. say north of west. Negative 53.1 degrees, that would be incorrect, because negative 3.51 degrees would say that was an angle from the positive x-axis in a negative direction. So actually saying negative 53.1 degrees would be down this way. And what we're really looking at is A plus a negative B.
It's like 8 from the y-axis be correct.
Yeah, is that, did I take off of that? Oh, okay. That would work, yeah. 36.8 or 36.9. Or if you had said 100, positive 126.9, then that would be correct. Degrees, and did this, and that would be correct. Any questions on that yet?
I put the angle as 140 degrees. That's right.
This number right here. Really?
Yeah.
I was, you shouldn't admit that. Well, if you feel up to it, you can bring it up to me to look at after class. Last problem, we had just worked on chapter 4 on the last day right before the test, so I made that the extra credit problem. I really had another doozy extra credit problem to do, but I figured, chapter 4. Over the weekend, I guess, for the test. So the soccer problem is very similar to the field goal problem. So you have to find the initial velocities and the x after cosine 30 degrees, which comes out to 26 meters per second. And initial velocity in the y direction is v naught sine theta. 30 times sine of 30. 15 meters per second. So you want to find the time it takes to the go. So you would say that the displacement in the x direction is average velocity times time. In this case, there is no acceleration, so your initial velocity is the same as your average velocity. So you could say that would be 0, and you have this from that. So your time is your displacement over your initial x velocity. 5 divided by 26, 0.192 seconds. So the goalie has 0.192 seconds. What? 0.2 seconds? 2 seconds. So, of course, the goalie has a little bit of anticipation working on his or her side. So. squared. This would be 15 times t plus 1/2. Acceleration would be negative 9.8 t squared. 15 times 0.192 minus 4.9 times 0.192. 0.67 or around 2.7 meters, which means it's going to be 0.2 meters above the net, and so the goalie probably shouldn't try to save it. You know, the goal, I mean, it's close enough so the goalie might want to try to poke the ball, but if always another dangerous situation, so you probably just want to let the ball go. Nobody explained that, but that would have been interesting if someone had. A few of you tried to use geometry to solve this, and that was commendable, but that wouldn't work. Ready for new stuff? Triple acceleration? Centripetal acceleration? We are going to do centripetal acceleration, but not, I'm going to stick that on with chapter 6.
Okay.
Because then we're going to talk about centripetal force.
Chapter 5. 4. I guess I didn't try to do it.
Here's the other one. That's a good one to look at. Any other ones from the first page? Any requests? Actually, I really think we ought to look at a couple of the other examples just because we haven't done any of these examples yet.
Chapter 4?
Yeah. And chapter 5.
No, chapter 4.
Yeah, that's pretty interesting. Well, let's start off with number 6 in chapter 4. It says an airplane flies horizontally with a speed of 300 meters per second and an altitude of 400 meters. Assume that the ground is level. At what horizontal we have an airplane, very aerodynamic. And the pilot's going to drop a bomb. Now, as soon as the bomb is released from the airplane, you'll have the same velocity as the airplane itself. So it'll have a horizontal velocity of 300 meters. question is how far, at what horizontal distance from the target must the pilot release the bomb so as to hit the target? Looks like a house, but it's actually a nuclear facility. So it's actually going to go through parabolic motion like that. At least horizontally, it's going to be unaccelerated. Look at these two motions that are happening simultaneously, but look at them separately. And our connection between the two will be time. The time to fall down to the level of the nuclear facility will be the same time that it follows forward. So if we look at it vertically, in the vertical direction, our acceleration will be 9.8 meters per second squared positive, because we're saying down is positive. And our displacement is going to be 400 meters. And we want to find time. That displacement equals initial velocity times time plus 1/2 acceleration times time squared. Initial velocity 0 because we're just dropping it. So our displacement is going to equal 1/2 acceleration times time squared. So time will equal 2 times displacement divided by square root 9.035. 9.035 seconds. So now we want to look horizontally. And we have displacement equals average velocity times time, which is just going to be x velocity times time. So that's going to equal 300 2.7 kilometers. So about a little bit more than 2,700 meters, or 2.7 kilometers. So you just calculate, it's going to drop 9.035 seconds. Need to release now, or hit 2.7 kilometers per hour. Greater respect for pilots who do this. Look at number 3. up here. To do that, to do it in a nice, rigorous way, what we need to do is find the tension in string number 3. And according to a free body diagram, we'll look at this object, this mass, which is 6 kilograms, and we're going to label all the external forces acting on it. Now on that mass, it's got weight. So there's weight pulling it down towards the center of the earth. And that weight which is actually the tension in the core, tension 3, that's pulling up. As I'm just focusing in on that mass, those are the only 2 forces acting on it. There's nothing horizontal going on. These other 2 tensions are way up here. They're actually not connected to that mass itself. So really it's just tension 3. Of all the forces acting on it, in this case in the y direction, would be equal to 0 because it's not moving. But there are actually forces on it. This just means that the sum of all of them equals 0. And we have a positive tension 3 and a negative weight. This would be tension 3 minus the weight. This would be, what is it? 58.8 newtons. All right, so now we know what tension 3 is. We'll focus in on the knot. And it looks something like this. We've got tension 2 pulling this way, tension 1 pulling this way, tension 3 pulling this way. Which means that the net force on it is 0 in any direction I look at. And in particular, I want to look at x and y. So T3 is cooperating because that's totally in the negative y direction. Would be, well, you know, they define that angle from the y direction, 60 degrees down. So I could say that component is T2 sine 60, but that could be very confusing. So probably the easiest way is just to redefine my angles. So that this would be T2 cosine 30. Magnitude, and this component going up will be T2 sine 30. This component vector added tip to tail of that component vector equals the T2 vector. X direction, and T1 sine 60. Up like that. And as a result of all these, it's 0. So in the x direction, I'm canceled out. T2 cosine 30 cancels with the T1 cosine 60. I could say that the summation of all the bring the T1 cosine 60 over here, and so I'll have T1 will equal cosine 30 multiplied by cosine 60 times tension 2. Let's just get a number for that cosine 30 over cosine. So I have two unknowns still, but I also have another equation to work with, so I need another equation. And that will be the vertical direction. So if I sum up all the forces in the y direction, going up on the knot, and I have one force coming down. So I have two positive forces, which will be T1 sine 60 plus a T2 sine 30 and minus T3. So we have the two positive forces and one negative force. So I could write this as 1.73 T2 sine 60 plus T2 sine 30 minus 58.8. So I plus sine 30 T2 and all that stuff. You probably went all the way to the end.
Yeah, T2, 29.
All right. So I guess all this stuff is 2.
Yes.
And now I can find tension 1. Tension 1 is 1.73 times tension 2. That's 1.73 times 29.4. And that is 50.9. So answer E. 51 Newton. What do you think? Let's look at number 2. So if M is 2 kilograms, what's the tension in string number 1? This is 1. Solve for your unknowns, and we're going to have to set up a free body diagram for the mass, and then a free body diagram for the knot. So we're just focusing on the mass first, and we'll say that my free body diagram, label all the external forces acting on it. I've got weight, mg, and they cancel each other out because it's not accelerating vertically. So I'd say the summation of all the forces in the y direction is 0. That's equal to tension 3 minus the weight. So tension 3 equals weight. It's 2 times 9.8, which is 19.6. And we focus in on the knot. It's got tension 3 pulling down. It's got tension 1 pulling across like this. Sorry, Dan, I'm running back and forth. As if you had two parallel lines and one line intersecting, the internal angles are equal. So if this is 30 degrees here, that would have to be 30 degrees there. Actually, T1 is cooperating. It's totally in the negative x direction. I don't have to break it up into components, x and y, because it's totally x. It's totally negative x. No y component to it. T2, I have two components. I've got a T2 tip to tail to make tension 2. So if I look at this thing, let's say vertically, summation of all the forces in the y direction would be 0. I only have one force going up in the y direction. That'll be T2 sine 30. And then I have one force and solve this for tension 2. So T3 equals T2 sine 30, and tension 2 equal T3 divided by the sine of 30, which would be 19.6 divided by 1/2, which would be 30. And if I looked horizontally, summed up all the forces horizontally according to Newton's first law, that should sum up to 0. And what do I have? I have T2 cosine 30 minus that's equal to 39.2 times 0.866, which is 33.9. So that's tension. All right, so let's take a look at number 4. If M is equal to 1.1 kilograms, what is the tension in string number here's string number 1 down here, and there's string number 2 there, and we want to find the tension in string number 1. This is a 40-degree angle here, this is a 40-degree angle there. You know, there. So it's not that that would help a whole lot, but just have to keep that in mind, that this is not exactly 180 degrees straight line. All right, so let's try it the same way. Let's focus in on the mass first. Find tension 3. Labeling all the external forces acting on it. Weight going down. Tension 3 going up. Summation of all the forces in the y direction will be 0, because there's no movement in the y direction. Say that's T3 minus the weight, mg. Is 10.8
8.
newtons. 10.8 newtons. And so now we're going to focus in on the knot. For the knot, I've got tension 1 coming down this way at a 40-degree angle. I've got tension 3 going down this way. Tension 3 is equal to 10.8 newtons. And I've got
That's supposed to be 50.
oh, yeah, that should be 50. Right. Which is probably the way I'd want to define it. It's 50 degrees from the x-axis. Thanks. And we want to find, what did we want to find? Tension 1? So what should I do? Okay, vertically or horizontally, or does it matter? Well, if I broke up tension 2, I'd have two components to it. I have a T2 cosine 50 this way, and a T2 sine 50 this way. Both of them in respective x and y positive directions. T2 cosine 50, T2 sine 50. Sine 40 this way. Actually, both of them in negative directions. I got one in the negative x direction and the other one in the negative y direction. If I look at things vertically, I would see that the only force I have going up is T2 sine 50. T1 sine 40 going down, and a T3 going down, all of T3. So I'm going to say a minus T1 sine 40 minus T3. Only thing I can simplify in that so far is that minus T1 sine 50 minus T1 sine 40. So far so good. One equation with two unknowns. If I look at the horizontal direction, I can get myself another equation. And cosine 50. And then I have a negative force, which would be a T1 cosine 40. So I could say then that T1 cosine 40, at least in magnitude, by the cosine of 40 times tension 2. Let's get a number for the cosine of 50 divided by the cosine of 40. 0.83. Over cosine 40. So now I have tension 1 in terms of tension 2. I can plug that into here and get myself one equation and one unknown, which is solvable. Sine 50 minus tension 1, which is 0.839, tension 2, sine 40. Factoring out the tension 2 in those two terms on the right, I got 10.8. All that times tension 2. What is all that? .227. .227. .47.6 newtons. Which is kind of nice to know, but we want to find tension 1. Tension 1 is 0.839 times tension 2. Times 47.6. Gives us 39.97, or I'll just round that up, 40.0 newtons.
Yeah, I couldn't read it.
I
You
couldn't
work
read
out
it.
with 37.
It's 37 degrees. Number 5. It's my usual 7 with the slash there. Recycle problems. We're going to do that for the environment. Recycle problems. Mess with that. What do you think? So far, so good? Stacks problems? Kind of happy? Let's try a dynamics problem. look at the example I have in my notes, I'm just going to work it on the board. It's actually a problem on your book. And does anybody happen to have their book with them? Fine. One. We're just going to make it up. We're going to set up a frictionless pulley, and we're going to put two masses against each other on this pulley. And so we'll have one mass, call it M1, and we'll say that the mass of that one, M1, is 3 kilograms. Is equal to 5 kilograms. The pulley is frictionless, so theoretically, all things considered, my expectation is that mass 2 being more massive than mass 1 and having a greater weight, then this system will move like this. These two masses and the tension in the string between them. So we want to find, let me write out the whole problem. We want to find the acceleration, and we want to find the tension in the string. Like we did with the status problem, we're going to draw free body diagrams. A free body diagram is a picture of the object as best as you can draw it, and labeling all the external forces acting on the object. So, if I do a free body diagram of mass 1, toward the center of the Earth. So mass 1 times G is its weight pulling to the center of the Earth. There's another force, there's a tension in the string pulling up on mass 1. And that tension is actually pulling on both ends of the string. So it's pulling up on mass 1. Right? But we're only focusing on mass 1 right now. So here's all the external forces acting on mass 1. The difference is that mass 1 is actually accelerating. It's not stationary. So Newton's first law does not apply. We can't say summation of the forces is 0. Mass 1, this system is going like this. mass 1 is actually accelerating up. So it actually has an acceleration that's going up, like that. That is what I call my free body diagram for mass 1, showing all the external forces and also indicating the direction. I will apply Newton's second law. Newton's second law says that if there is an acceleration, the summation of all the forces, the net force, will equal not 0, but mass times acceleration. So we're going to say the summation of all the forces, in this case in the y direction, will equal the summation of all the forces. And there's only two. I got positive t going up, and I have a negative m1g going down. So I'll say that this is t minus m1g. So I chose up as positive. As we'll see on the next mass, when we set that one up, the acceleration will be going down, and I'll choose down as positive. Whatever direction the acceleration is going, that's the direction of my net force as my positive direction. So there's my equation. Mass 1 is 3, so we have 3a equals tension minus 3 times 9.8. So I have 3a equals tension minus 29.4. I have one equation with two unknowns. I don't know acceleration. I look at mass 2, mass m2, and do a free body diagram of it. Mass is 5 kilograms. There's two forces acting on it. It's got weight, and it's got tension pulling up, same tension actually. It's going down. As it turns out, the value of that acceleration will be the same as the value of this acceleration for mass 1 because they're connected. Whatever this is doing in terms of displacement, this one will do in terms of displacement. Velocity, you have to do the same, only in opposite direction. Right? So here's my free body diagram of mass 2. That helps me set up the equation for it. Since it is accelerating, Newton's second law applies. So I say the summation of all the forces in the y direction. So what is the summation of all the forces in the y direction? Well, I've got weight m2g going down, and I got tension going up. I want the net force in the direction that the acceleration is going. So I assume the positive direction is the acceleration direction. So my positive force would be m2g. In the direction of my acceleration. Putting in the values for m2, then I have 5a equals 5 times 9.8 minus tension times 5a equals 49 minus tension. From the first equation, I had that 3A equals tension minus 29.4. So I'm just going to write that right below this. Now I have two equations and two unknowns. I could solve for, say, A in one and then plug it into the other. Or I could solve for T. 5A equals that, and 3A equals that, and this equals this, and that equals that, and this plus that equals this plus that. Right? So I'm going to add all the left-hand side together, all the right-hand side together. If they're all equal, then it should remain equal. So 5A plus 3A is 8A. T will cancel. So I have 8A equals 19.6. A 19.6. So A will equal 19.6. meters per second squared. So essentially, because we have this counterweight, mass 2 does not just fall under gravity 9.8 meters per second squared. With the counterweight there, it actually accelerates down at 2.4. If I want to find the tension, now that I know the acceleration, I can plug into either one of these and solve for the tension. So I could say that since 3A equals T minus 29.4, T will equal 3A plus 29.4, which is 3 times 2. Or 36.8 newtons. And that would be the tension in the core. Sound good? That's one way to do it. Sometime. Here's my situation. Here's the same problem. Mass 1 is 3 kilograms. Mass 2 is 5 kilograms. We've been using the second law on this. So we add up the net forces on an object, and we set that equal to MA. Let's try this. Let's make the two masses part of one object. All right? Let's make them part of the same object since they're connected, and if this one moves, this one moves. Let's just put them say a bag, and you wouldn't be able to see the individual masses. You would just see this one blob move like that. All right? If I did that, I could say that the mass of this one object would be 8 kilograms. And if I were to look for the external forces acting on it, of course I would have an M2G over here pulling down on it. And I would have an M1G pulling over here, pulling down on it. The tension I wouldn't have to worry about because the tension's inside the object. It's part of the object itself. All right? So the way I would describe that using Newton's second law is, because this is my free body diagram right here, I would say the summation of all the forces equals total mass times acceleration. And in the direction of the acceleration, which I've shown to go this way, I would have m2g it down in the direction of acceleration. So m2g minus m1g. If I put in my numbers, then I would have 8a equals m2, which is 5 times 9.8 minus 3 times 9.8. That in my head, that would give me 0.45 meters per second squared. Kind of nice, huh? So in just a couple steps, if I think of it this way, I can get the acceleration right away. So if I want the tension, what I could do is then go back to the original situation, just do a free body diagram of either mass 1 or mass 2, set up one of these original equations, and then plug in that acceleration and get the tension. So it's still shorter. I would just have to focus in and do one of those free body diagrams for mass 1 or mass 2. Let's just try this out on problem number 7 in the handout. It says the horizontal surface on which the object determine F. So we and tension 2 we don't know, but we do know that the mass M is 2 kilograms. So let me kind of rewrite this. It's 2 kilograms. And pull along by some F we don't know. We do know tension 1 is 12 newtons. Couple minutes, I'm going to show you the very shortest way to do this problem, and then let you think about it. Think about the other possible ways. But first of all, this whole thing is accelerating, right? And everything's connected. So everything is accelerating with the same value to the right. Say the Golben method to just these last two here. If I were to focus in on just these last two masses here and treat them together, I would say that here's a total mass of 6 kilograms, and it's got weight, mg, and it's got a normal force. When the direction that it's going, so say 12 newtons, yes. It's only connected by this cord 1. Right? I mean, F is over here, it's connected to this 4 kilogram mass. As far as this mass right here is concerned, there's only this one cord, which we know is tension 1. And we know it's 12 newtons. MA, and that's equal to the net force in that direction. There's only one, tension 1. So I could say that tension 1 equals MA kilograms here. So we're going to say that that's 12 newtons divided by 6, or 2 meters per second squared. So the acceleration is 2 meters per second squared. And that would apply to all 3 of these, because they're all moving at the same acceleration. The whole thing now. So let's do this. Look at the whole thing. We got this one force F pulling the whole thing out front. Tension 1 is now internal to the whole thing. And the total mass is 10 kilograms. So I encompass the whole thing. Now if I were to is equal to MA, and that's now equal to F. That's the one force making it go. So F equals MA, got to be 10 times 2, or 20 newtons. What do you think? Try your hand at those. In columns 8, 9, 9's on an incline. We haven't done friction yet, so I haven't introduced friction. But up through 15, we'll take a look at those. And we'll see you next time.